Okay, so here we go. Here's the objectives. Or here's the title, I guess. Write it down. Continuity is how you say that? Continuity? Continuity. Or if you're from Utah, you say continuity. And one-sided limits. That I was born and raised here. But we don't pronounce T's for some reason. We say mountain and fountain and continuity. Anyway. So I want you to write down these objectives, but let's abbreviate it a little bit. Determine continuity on an open interval. That's your first objective.
Are you recording?
Yes. Thank you for reminding me. So continuity on an open interval. Come on, Frank. Continuity on an open interval. And then we got to talk about one-sided limits. That's the second objective. One-sided limits. Does anybody have an idea of what that might be? A one-sided limit? What were you saying, Danielle? Natalie. You're Danielle. It comes from a just one side, right? Didn't we talk about last time the limit has to come from to the same point on both sides?
Yeah.
Okay, that's a full limit. A one-sided limit, you just approach a point from one side, either the right side or the left side. It has its uses. Properties of continuity. And then we have this cool little intermediate value theorem. It is pretty cool. So, I think we can get through all this. Holy cow. There's a lot. Go back. No. We're going to get through all of this, dang it. It's the next math class. Alright, let's talk about continuity. I've talked about this briefly. I didn't talk about it in terms of continuity, but I don't know if it was last time or the time before. Do you remember me mentioning really briefly that if you took your pencil and can trace an entire graph without lifting up your pencil, remember what I called that? It's a continuous function, right? If you have to lift up your pencil and then start over again, there's discontinuities somewhere on the graph. Like that could be a hole, right? What other times on certain types of graph would you have to lift up your pencil and then start again somewhere else? A piecewise function, what were you saying? No, in the other direction, yeah, it's a piecewise graph, you're right. What if we have a graph that is continuous, except at one point there's a little hole? You got to lift up your pencil, right? So that would be what's considered discontinuity. Anyway, we've talked about it a little bit, but you don't need to write down this whole thing. Write down the bottom piece of it, though, about continuity. So write definition of continuity. The graph is unbroken. There are no holes, jumps, gaps. Now, the way that you need to think about continuity is not whether the entire graph is continuous, but at a certain point of the graph, at a certain location of the graph, is it continuous at a certain point? You understand what I'm talking about? At a particular point on a graph, is it continuous? Well, how do you know if it's continuous? There can't be any holes, there can't be any jumps, there can't be any gaps at that one point. Okay? It is. Discussing continuity is pretty easy. It really isn't that big of a deal, but it is important for the study of calculus. So, jot down those pictures real quick. These are different types of discontinuities that can occur. Just do your best to draw a quick picture.
These ones are not continuous at these values of C. Here there's a hole in the graph. Here there's a gap. It jumps from up here to go way down here. And this is another type of discontinuity. The direction we're heading with this eventually is trying to tie this into limits and continuity. There's a couple of key things here that I don't want to overlook, and I don't want you to overlook them either. We're not considering the entire graph on these. Like this first picture right here. Where's my mouse? It's gone. Does anybody see my mouse on there? Oh, there it is. So this graph right here. This is just a piece of the function starting at A and ending at B. Do you guys understand that? This is not the entire function. So when we're talking about the continuity of a function, you have to have an interval. And this is called an open interval. Do you understand the difference between an open interval and a closed interval? What's the difference? Open and closed? What does that mean? Whether the endpoints are included. Right? So this little interval here that has the parentheses a comma b, that's an open interval. When we're talking about the continuity at a function between a and b, we don't include the endpoints. So this is a piece of the function not including the endpoints. There's a discontinuity there at c. So the graph is not continuous at c. If let's say that somehow I was able to take this value of b and drag it way over here, would the graph be continuous on that interval from a to b if I were able to move that b value to where my mouse just was? Yes. It would be continuous on that open interval from a to b because there's no discontinuity. But as it is the graph continuous at c on the interval from a to b for this function? Is it continuous at c? No, it isn't. Because there's a gap there, or a hole. Here there's a giant gap. Here there's a gap. There's a point down here. Anyway, these are just what some of the discontinuities could look like. So just jot those down. Those are conditions for discontinuity. The function is not defined. The limit does not exist. Or the limit does exist, but it's not equal to f of c. You need to write these down. I'll talk about what these mean. These are conditional. These are conditions of discontinuity. This is what happens if there's a discontinuity. These three things cause discontinuities. That means the graph is not continuous. If the function is not defined at x equals c, then there's a discontinuity. That means it's either a hole or a gap or a jump or whatever you want to call it. There can also be a discontinuity if the limit doesn't exist as x approaches c. It might approach one value from the left, but approach a completely different value from the right. So if the limit doesn't exist, then obviously there's a gap in the graph somewhere, so it's not continuous. There's a discontinuity there. The third one's kind of hard to wrap your head around at first. The limit exists, but it isn't equal to f of c. That means it wouldn't be the same thing as if you had used direct substitution. The limit is there. Here's what that is. Let me just go back. I'll let you write that down in a second. You see this third graph right here? As I'm approaching c from either the right or the left, does the limit exist?
Yeah.
It approaches this open circle right here, right?
Oh, yeah.
But is that the value of f of c? If you were to plug in c into the function, is that the value of f of c? The value of f of c is way down here, that little black point down there. Does that make more sense now, that third? The limit exists, but it's not f of c. They're different. Okay? If that's the case, there's a discontinuity. There's a hole there, and the graph is
defined just below it in that case. So if any of these things are present, there's a discontinuity. If none of them are true, the graph is continuous everywhere on that open interval. It may not be continuous everywhere on the function, but just on that open interval, it's continuous at C. So, in your notes, you should write definition of continuity. These three things must be true. You have to be able to evaluate the function at f of c. You have to be able to find the limit as x approaches c. And not only that, you have to be able to find the limit using direct substitution. The limit of f of x as x approaches c is just f of c. So it's called continuity at a point. If it's continuous at a point, all of those have to be true. You have to be able to evaluate the function at that point. F of c has to be defined. You have to be able to find the limit using direct substitution. Some functions are continuous everywhere, like quadratic functions, right? The parabolas, they're continuous everywhere. There's no. What other type of functions are continuous everywhere? Everywhere continuous. Linear functions, cubic functions, any polynomial function, anything x to the 4, x to the 7, any polynomial function is continuous everywhere. Where are we going to run it? Let's just talk about the type of functions that are going to give us trouble in terms of continuity. We've seen them before. Rational functions, piecewise functions. Where else might we have? Tangent. Some of the trig functions, definitely tangent and cotangent. We're going to get into that into the next unit. Okay. And then there's some really, really weird functions that we haven't seen that just have certain discontinuities. All right. From this page, back. So, really all you need to write from here is this third sentence, discontinuities. There's two types of discontinuities, removable or non-removable. Write that down. Discontinuities, there's two types, removable, non-removable. We saw a little bit of this last time, I think. Yeah, it was last time. A discontinuity is removable if it can be made continuously by redefining f of c. All that means is rearranging the formula, factoring things out, multiplying by conjugates, that sort of deal. Remember doing that last time? If there's a discontinuity that's removable, that means you can rearrange the function, redefine it at f of c. Okay? Yeah. Yeah. We don't really need to do that. Page isn't super important. Finally we have some examples. Here we go. This is exactly how homework starts. Well, it kind
second homework.
Discuss the continuity of each function.
We're going to skip part D. We're not doing trig yet. That's the next unit, so don't write down part D. Leave some space in between those, though. We got to write a few things. In the sense that they didn't give us a specific interval to consider continuity on, we just consider the continuity of the entire function on its entire domain. So part A. Yeah.
So you're saying an interval is like a
Certain part of the graph. Yeah. So they may ask you to determine continuity on the entire domain of the function, or they may say, well, from here to here on the function is a continuous or a discontinuity.
So for part A, since we weren't given an interval, just anywhere on the graph of part A,
Is there going to be a discontinuity, a break in the graph, a gap somewhere, a hole? Right on the y-axis, right?
so rather than saying it's continuous everywhere,
You would say you just want to state the one discontinuity. Where is there a discontinuity? X equals
0. You would say there's a discontinuity at x equals 0. Just curious, does anybody remember
the graph of that looks like. It was something that you looked at last year. 1 over x. Anybody remember?
Yeah, it kind of looks like, I don't know if I can write on this or not. Let's see. Kind of, yeah, I can write on this. So the graph of this, there's, do you remember what that funky word was? Starts with an A. There's an asymptote running through the y-axis. Okay? And the graph will look something like that. What about g of x? X squared minus 1 over x minus
1. What do you think?
Discuss the continuity. X squared minus 1 over
X minus 1. There's a discontinuity at 1. How come? It's undefined at x equals 1. You couldn't plug in a 1 to that function, right? Now, let's refer back to that removable versus non-removable discontinuity. Couldn't we change that a little bit? X squared. Go ahead and try it. Back to the numerator.
when what's his face here comes back.
Yeah, very good. Yeah, you can go.
So,
Were you able to remove that issue causing the discontinuity, that x minus 1? Were you able to remove it somehow?
Yeah.
So it's still a discontinuity, but what kind of discontinuity is it? Removable. There's non-removable and removable. Part A, what would you have classified that as? Non-removable. There's nothing we can do with it. It's discontinuous.
because it has that vertical asymptote right there.
But on part B, the graph just looks like this on part B. It's essentially linear, but it has that one hole right there at the discontinuity of x equals 1.
That's what's considered removable discontinuity. It's still discontinuous. It's still a discontinuity, but it's just a removable discontinuity. What's that? You would have to rearrange it and then find the limit as x approaches 1.
It's not continuous at x equals 1. It's continuous everywhere except where x equals 1. There's a discontinuity.
X equals 1. You'd say there's a discontinuity at x equals 1 in here?
And Dan's question was a good question. How do we know exactly where the discontinuity is? Well, it's at x equals 1, but how do you know where the y value is? How do you know it's exactly right there?
So you can put it in the equally
You could graph it, yeah. But,
direct substitution.
well, the problem with direct substitution in the original function is if you plug in a 1 right here, so you would have to redefine it. Because what happened when you crossed out the common factors? What did you end up with? X plus 1?
Yeah.
So then if you plug in a 1 to that, you get 2. So it's, what's that?
That's the y value. Yep, that would be the y value there. Alright, that's a good chunk of your homework right there, discussing discontinuities. It has another example. Oh, just gave you the answer. Shoot. Alright, part C.
What about that one? Piecewise. Let's put those away. Yo. What about part C? Usually, now I'm saying like 99% of the time on piecewise functions, aren't there pieces everywhere that aren't connected?
Yes.
Usually. So, can you always just assume that because it's a piecewise function, there are going to be discontinuities? Most of the time, yes, but you can't just say, all right, it's piecewise, there has got to be a discontinuity there. We got to take a look at what this graph looks like.
So let's graph part C. Graphing piecewise functions is so fun. Okay, tell me how. This is something you guys did last year.
So x less than 0 or equal to.
Never graph a piecewise function. You a little fuzzy on piecewise function graphing?
No, Braden knows it.
Braden knows it?
Graph it right now.
Yeah, we're graphing this part C right here. We're not doing part D, it's a trig function. What do you,
One would be a closed in dot at +1, or y. 0, 1, 2.
at 0, 1, there's going to be a closed dot there, yeah.
Would be a line to the left.
And it's going to be going to the left with a slope of... That's one way you can do it. You can think about it that way. Honestly, you guys, this is the easiest way I have found to graph piecewise functions. You ready? Let's make a quick little table of values just relating to that piece right there, an XY chart. What are some of the X values I can use there? What? I can use 0. What else can I use? -1, -2. All right, let's use those as X values. Why did we choose these particularly? Because they fit the domain. X has to be less than or equal to 0. So at x equals 0, we're going to have a y value of 1. Open or closed? Closed. At an x value of -1. So -1 comma 0. So we have a point right there. And at -2? -1. So we have -2 comma -1. So that piece of the function is linear. It looks like that. What kind of a piece of a graph is this going to be x squared plus 1? What kind of a... That's quadratic. So all this is, that's going to just be a piece of a parabola. All right, let's do the same thing. Let's make a quick table of values for that. What's the first value of x we should use?
0.
I'm going to use 0. Now, you might argue, well, it can't equal 0, and you're right. It's an open dot, exactly. So I'm going to put that. You got to remember that's an open dot right there. So if we were to plug in 0 right there, what would we get out of that? Now what? It's an open dot on a closed dot. That's a big open dot. Anyway, so we have 0, 1. Where else are we going? Let's go 1. 1 squared is 1. 1 plus 1 is 2. So we have 1 comma 2. Let's do one more. 2 squared is 4 plus 1 is 5. So we have 2 comma 5. So it looks like we just have the right piece, or the right half of that parabola right there. So going back to what we were just talking about, usually
There are discontinuities on piecewise functions because there's gaps everywhere. What happens when you have a closed circle right inside of an open circle? what supersedes what there? It's just a closed circle. Okay? So when we consider that graph, are there gaps or holes or breaks anywhere?
No.
So how do we discuss the continuity there? Are there discontinuities?
No.
So it's continuous.
Got him? Let's see if we can scroll over here. Ooh, a lot of writing. Where's part C? Oh, there it is. Right.
So it's continuous. You can say it's continuous everywhere, or it's continuous on the, they say entire real number line, but it's continuous everywhere.
Okay. That one, could you have known that just by looking at the equations?
Well, possibly, I guess. If you're really, really good at thinking about piecewise functions. Best thing to do, though, just to be safe, what's the best thing to do with piecewise graphs? Make tables and graph them, just to be safe.
Usually you are going to end up with a gap, but not always. Okay. Ooh, trigonometry. Doesn't this look fun? We're going to get into this next unit. Man, that looks awesome. Graphing trig functions is the best. All right, one-sided limits. Here we go. You know what? This thing is taking way too long. Let's just get back to the whiteboard. I'm not liking these. Here we go. I'm just going to write. One-sided limits. So, draw two graphs here. And draw another graph here. X approaches C from the right. That means the graph is coming at it from the right, so it's moving to the left, coming from the right. On this graph, X approaches C from the left. So it's coming from the left, moving to the right. So the notation, if it's coming from the right, the notation for that is this: the limit as X approaches C with a little plus sign above it like that. The limit as X approaches C plus. Why did they put a plus sign there, do you think? It's coming from the positive side, moving towards the negative side, right? So the limit as X approaches C plus of f of X equals L. That's just a notation from a right-handed or a right-sided limit. As X approaches C from the left, the notation is X approaches C minus. It's coming from the negative side, headed towards the positive side.
What's L again?
L is just whatever the limit is. Whatever the value of the limit is, that's L. So for example, this is a funky graph. F of X equals big square root of 4 minus X squared. I want you to find, or we're going to discuss, find the limit as X approaches -2 from the right. So we're doing a one-sided limit. So we're not coming at -2 from both sides of the graph. We're only coming at it from the right side. Let's draw a graph first of all. Just for sake of time, and this is something you guys would be best to start recognizing, because you see this type of a function every now and again. It's just one of the halves of a circle. Okay, and here's why. You need to think back to, it was later on in pre-calculus, but x squared plus y squared equals 4. Isn't this the equation of a circle? With what radius? Careful, radius is 2, right? Well, how do we go from here to here? Well, if you solve for y, you're going to subtract x squared, so that's going to be minus x squared, right? And then what are you going to do? You're going to square root both sides. So look what we have. That was the equation of the circle. Why is it only half? Because it's a function, right? What if we had the full circle? Not a function. That's why we only take, in this case, it's going to be the top half. Now, what was the radius? What did we say the radius was? 2. So starting from 0, 0, we're going to go out to, over to, and up to. I'm the worst circle drawer. Ooh, that was actually not bad. Just the top half. Because that's a good question. Normally when you take a square root, there's going to be a plus or minus, right? But we just took the plus and not the minus. So that would be the top half. The minus would be the bottom half. That makes sense. So, well, we could have had the bottom half and you still could have approached it from the right. They only gave us the plus and not the minus. Yeah. So anyway, you're asked to find this. Find the limit as x approaches -2 plus of f of x. Now let's talk about the graph first of all. Just looking at the graph. What is it? As x is approaching -2 from the right side, where is the graph heading, or what's going to be the value of the graph as x is approaching -2? So I'm traveling along the graph, right? Am I approaching -2? Where's the graph approaching? 0. Okay. Why did we have to do a one-sided limit at x equals -2? Why a one-sided limit? Why couldn't we just do a full-blown limit? Why? This is important, you guys, to think about. Why did we have to do a one-sided limit at -2?
There's not another side, right? Remember the definition of a limit, it has to come at it from both sides? Could we come at -2 from both sides? No. So we do a one-sided limit. One-sided limits are great
when we're talking about radical functions. This is a radical, because quite often a radical function will have a starting point and then move off. This looks familiar, right?
Yeah.
Could I talk about a limit right here? I could talk about a one-sided limit, right? Could I talk about a full-blown limit?
No.
No, so these one-sided limits are great for radicals. But anyway, let's answer this. What's the answer here? F of x approaches what as x approaches -2 from the right?
0.
0.
Could you just do substitution?
Let's talk about that. Would direct substitution have worked? Plug in a 2, or a -2 rather. Plug in a -2, square it. What's -2 squared? 4. 4 minus 0, or 4 minus 4. Square root of 0. 0. So as long as it's defined there. Say that again. The plus or minus. I see what you mean. They wouldn't really have ever done that, because in that case it wouldn't have been a function. We're only taking limits of function. That's a great question. Yeah, that would have been a full circle, because if they had given us the full circle, then we wouldn't really know where to come at as x approaches -2, because we could either come at it from there or there, so it just get really confusing.
Are we going to look how to find limits of non-functions?
Nope, just functions. We just talk about functions.
Yeah.
Okay, here's a theorem. Existence. Ooh, how do you spell this? Existence of a limit. We're talking about full-blown limits, limits from either side. We got to write fast. We've got just a few minutes left. Let f be a function. Let C and L be real numbers. The limit as x approaches C of f of x is equal to L. And again, that capital L just means whatever the limit is equal to L, if it exists. This limit exists and equals L if, and only if, this has to be true. Basically, what is this saying? It's a lot of scientific mathematical talk. Really, let's make it more simple. What is this saying? A full-blown limit, which is what we started with, the limit as x approaches C equals L. That limit only exists and equals L if what? If both one side of the limits equal the same value. So if both of the one side of the limits equal L, that means the full-blown limit equals L as well. Okay? We just put it into a math definition. We got to go over this intermediate value theorem real quick. Intermediate value. This isn't going to take very long. This is pretty easy. There's no objective. Yep, this is the last objective. If f is continuous on a closed interval now, a, b, so this includes the endpoints, and f of b does not equal, sorry, f of a does not equal f of b, K is any number between f of a and f of b Now, let me stop here for a second so you don't get too lost before I finish this. At some point, a lot of these definitions have to start making a little more sense when you read them, because the wording on the AP test or AP exam might have this kind of terminology, and you got to be able to make sense of it. What are A and B? Numbers, right? They're from here to here, A and B. If you take a number and plug it into a function, what do you get? Another number, right? So this right here, f of a, what is f of a? It's a number, right? What is f of b? It's another number. Where is k going to be? In between a number and a number. You understand what this is talking about?
Yeah.
So k is just any number between f and a and f of b, but those are just numbers as well. So k is between just 2 points. And we can't have f of a equaling f of b. Okay, we okay so far? Okay, so if k is any number between f of a and f of b, then there is at least one number c in the closed interval, so C has to be between A and B somewhere. Such that f of C is equal to K. Let's make a quick drawing, real quick. So let's say that this is A, let's say that this is B. That point, this is f of A right here. That's f of B. So is the graph continuous from A to B? Including the endpoints? Okay, so what this means is if I chose any number C, let's say I chose C right here, and then I evaluated f of C, then I'm going to get K, and K is going to be where? In between f of A and f of B, and the point here is wherever f of A is and f of B is, those are just numbers. Are they the same number? No. They're not the same number. So the point is, couldn't I choose any C value so I could eventually get all the numbers between f of A and f of B? Yeah. Does that make sense? If I wanted to choose, I don't know, this number here, for example, you see where that x is? Then couldn't I find a C somewhere between A and B so that if I plug that into f, I could get that number exactly? Yeah. Let's say that f of A was 3 and f of B was 10. You following? Okay? If I wanted to get all the numbers between 3 and 10, then according to the intermediate value theorem, there's some number C between A and B that's going to allow me to find that. Because, what's the point here? Why am I going to be allowed to find that? F is what? Because f is continuous, if I wanted to find any value between f of A and f of B, then there's going to be some number C that's going to allow me to do that. I could find any value between f of A and f of B because it's continuous. Now, it doesn't really have a ton of uses except for one in particular, finding zeros. This is really, we're approximating zeros, I guess is how you use it. We'll see how much into this we can get. We might have to cut this off short, but use the intermediate value theorem to show that this function right here has a zero. What do I mean by zero? What is a zero? An x-intercept. All right, so we have to show that it has a zero in the interval. Zero, 1. All right, we have 1.5 minutes. Here we go. I'll explain a little bit of this next time so we don't just end it so rushed. What's f of 0? It's -1, right? F of 0 is -1. What's f of 1? 2. So plug in a 1, we get 1 plus 2 minus 1. What's the significance of this, you guys? This is pretty significant. F of 0 is -1. F of 1 is +2. What does that mean? How do we know that? How do we know that there's an x-intercept between 0 and 1? Because f of 0 is a negative number, right? So that means it's below the x-axis. You follow me?
But f of 1 was a positive number, so all of a sudden now the graph is above the x-axis. It was below here, it was above here, so what had to happen? It had to cross through. And where does it cross through? Somewhere between 0 and 1. Okay? How does the intermediate value theorem help us? Well, we know this graph is continuous, right? How do we know this is continuous, by the way? It's a polynomial function. So if the graph is continuous everywhere, then if it's negative at 0, f of 0, but positive f of 1, it had to cross through because it's continuous. Anyway, we'll have to pick this up next time.